Ever wonder how AI image generation got so ridiculously fast? I mean, it feels like one day it took minutes, and the next, poof, seconds. Well, today, we're going to pull back the curtain on the brilliant mathematical idea that made it all happen. It really does feel like magic, doesn't it? You type in some crazy prompt, a cyberpunk city made of candy, and just moments later, you get something absolutely stunning. This stuff has just exploded. But here's the thing. Behind the scenes, the first versions of these diffusion models were, well, they were slow. Painfully slow. We're talking several minutes to generate one good image, which would just hog a super powerful computer. It was a huge bottleneck. So what changed? How did we get this incredible speed up that turned this thing from a niche research project into something we can all play with on our phones? The answer isn't just, faster computers. It's way cleverer than that. It was all about a fundamental shift in perspective. Researchers totally reframed the problem. They stopped thinking about it as a series of clunky individual steps and started seeing it as one single, elegant, continuous motion. And, well, that changed everything. Okay, so to really get the solution, we've got to understand the original problem. Let's take a look at how these models used to work, the slow, old-school way of making a picture. The whole idea is called a diffusion model, and it's basically a two-part dance. First, you have the forward process. You take a perfectly good image and you just keep adding a little bit of noise over and over until it's nothing but TV static. Then you've got the reverse process. You train an AI to do the exact opposite, to start with that static and carefully, step by step, remove the noise until a brand new image appears. And this is where the big problem was. To get a really sharp, high-quality image, the AI had to take a ton of tiny little careful steps, like 1,000 of them or even more. Sure, you could take fewer, bigger steps and it would be faster, but the image would look, pretty bad. So you were stuck in this trade-off, good and slow or fast and garbage. This whole dilemma led some very smart people to ask a really fascinating question. We know more steps are better, so what's the most extreme version of that? What if, instead of just 1,000 steps, we could take a truly massive number of steps? What if we could take an infinite number of infinitely tiny steps? And that question, that little what if, was the spark. It completely changed the game, moving the whole field from thinking about individual steps to thinking about a continuous, unbroken flow. This is the absolute best way to picture it. The old way was like walking down a really long, clunky staircase. Every single step is a separate action, a distinct calculation. The new idea? It's like sliding down a perfectly smooth ramp. It's just one unbroken motion from the static at the top to the perfect picture at the bottom. So, that smooth ramp is described by something called a stochastic differential equation, or STE. Now, I know that sounds super intimidating, but don't worry, we are not about to solve any equations here. All you need to know is that it's just a fancy name for the rules of that smooth path, a path that has a clear direction, but also has a little bit of randomness sprinkled in. So why does this matter? Well, by thinking of the problem as an SDE, researchers weren't just using fancy words. They were basically unlocking a secret door to a whole new mathematical toolbox, one that's been used for decades in fields like physics and engineering. And this new toolbox gave them two massive advantages. First, they could create a predictable superhighway from noise straight to an image. And second, they got access to way smarter ways of traveling down that highway, which are called solvers. Let's talk about that superhighway first. It turns out, if you just take the random part out of the SDE, you're left with something called an ordinary differential equation, or ODE. And this creates one single, perfect, predictable path. The cool part? Now, if you start with the same static, you get the exact same image every single time. The process becomes totally deterministic. Okay, so the other huge win was getting access to these advanced solvers. Now, a solver is just the algorithm that does the math to figure out where to go next on the path. The original models used a really basic one, but this new SDE framework opened the door to much more powerful options. Let me show you what I mean. A simple solver, which you see in step 1, it just looks at where it is and takes a simple step forward. It's kind of naive. But an advanced solver, well, it's a lot smarter. In step 2, it takes a little peek into the future, a small test step, to see where it might land. Then, in step 3, it averages its original direction with the direction it found from that future spot. And finally, in step 4, it uses that average to take a much more accurate,
much more informed step.
Now, you're probably thinking what I was thinking. Hold on a second. To take that smarter step, the computer has to do twice as much work for every single step. Doesn't that just make it slower? And that's a perfectly logical question. It really seems like we're just making it more complicated.
And this is the beautiful, mind-bending part, it doesn't. Even though each individual step is twice as expensive to calculate, those steps are so much more accurate that you need way, way fewer of them to get to the same quality image. It's like taking giant, confident leaps instead of 1,000 tiny shuffles. It is way more efficient overall.
So, let's put this all together. What does this mathematical wizardry actually mean in the real world? Let's look at the payoff. I mean, just look at this chart. The original models, they needed around 1,000 steps to make a decent image. With one of these advanced solvers, you can get an image that's just as good, or maybe even better, in only 20 steps. 20! That's a 50 times reduction. This right here is the speed up that we all feel when we use these tools today. So why does all this matter to you? Well, it means you get your images in seconds instead of minutes. It means you get better looking pictures more efficiently. And really, this is the big one. It's what made this incredible technology go from a lab experiment to something powerful enough and fast enough for everyone to use, powering tools like Stable Diffusion that have changed the game. The real takeaway here is just so cool. The breakthrough wasn't a bigger computer or a more complex AI model. It was simply a change in perspective. By learning to see 1,000 clunky steps as one smooth, continuous flow, researchers could grab a completely different and way more powerful set of tools to solve the problem. And that kind of leaves you with one last big question, right? This one shift in thinking completely revolutionized AI art. It makes you wonder, where else is a problem just waiting for a similar change in perspective? What other clunky step-by-step processes out there could be turned into a smooth flow to unlock the next huge breakthrough? Pretty amazing stuff to think about.